In this video, we're going to introduce polar coordinates. Although Cartesian coordinates are familiar, it's sometimes easier to use something else depending on what you're trying to solve. So we're going to be taking a look at the polar coordinate system. And before I talk about anything, essentially with all coordinate systems, in this case, we have a 2D coordinate system. We have our x and our y axes and some random arbitrary point here, point P, which is represented by x and y across. And if we're switching to different coordinate systems, all we're doing is trying to find a different way to represent that point over there. So maybe I can travel across this x direction a certain number of units and then move up a certain number of units in the y direction. But maybe another way would be to draw a direct line to point P. And once we draw a direct line to point P, that line is going to be at an angle to both the x and y axes. So that's another way of looking at coordinate systems and specific points. So the polar coordinate system is just another way of representing a specific point on a specific plane or space. The first thing I want to do is to redraw that diagram that you just saw. So we're going to go through an overview of polar coordinates. So we have the x and y axis. We have the origin here, right at the center. And let's draw a point P. In Cartesian coordinates, this point P is represented as a coordinate of x, y, because it means that you've moved an x distance away from the origin in the x direction, and you've moved a y distance away from the origin in the y direction. And this would be at a right angle to each other. So with the path you take in the x and y direction, you end up at point P. That would be the Cartesian coordinate system. However, we want to find a different way of representing this. So as I've said, you can connect O and P together and call R the distance between O and P. In other words, R is the distance P is away from the origin. So if I have this distance R, how can I relate it to x and y so that I end up at P? It means that I have to introduce a new angle called phi, and with that, I'm able to arrive at my point P by saying it's a certain distance r away from the origin, rotated at an angle of phi from the x-axis. So I can represent this as r phi. So this would be our polar coordinates. And as you can see from this graph, there's a right angle triangle. So there are a few relationships that we can get from here. From a right angle triangle, we know that there's Pythagoras, so we have x squared plus y squared equals to r squared. We also have different trig functions that we can analyze. So we have sine of phi being equal to opposite y over hypotenuse r. This gives us y is equal to r sine phi. We have cosine of phi being equal to adjacent over hypotenuse, and x is equal to r cos phi. Last but not least, we have the tangent of phi, which is simply sine phi over cosine of phi, which is y over r over x over r. And that means the tangent of phi is equal to y over x. So as you can see, through these four equations, it is possible for us to easily convert back and forth between polar and Cartesian coordinates. So the next thing we want to talk about is why polar coordinates are useful. So we're going to go through two exercises of calculating the area of a circle. And that basically means using two different methods to figure it out and finding which one's easier or more convenient. So let's calculate the area of a circle. So we're going to compare two methods. The first method is going to be using Cartesian coordinates. And the second method is going to use polar coordinates. So why don't we start off with Cartesian coordinates and see if it's easy or hard. So with Cartesian coordinates, in order to find the area of a circle, let's first draw it out. We have the x-axis and the y-axis, and we have our circle. The best way of going about this, and the easiest way, is to probably break up our circle into 4 different areas, or quadrants. So let's split this up into 4. We have quadrant 1, 2, 3, and 4. So it makes sense for me to try and figure out the area of quadrant 1 and then multiply it by 4 because of symmetry in order to get the total area of a circle. So I can say the area of a circle is going to be equal to 4 times the area of Q1. So now we just have to figure out how to find the area of Q1. And if we're using Cartesian coordinates, it means that we need to look at a differential surface element ds. So what this means is if we're using Cartesian coordinates, it means that we can only move in the x direction and y direction. So any changes that are happening must happen in the x direction and then the y direction. And because of this, we have dx and dy, and we have this differential element called ds, which is equal to dx times dy. So that means there's a tiny step in the x direction and a tiny step in the y direction. The smaller the step, the better the approximation we have. And we just add up all of these tiny little areas to get the total area of Q1, and then multiply by 4 to get the total area of the circle. So now that we know ds is equal to dx times dy, we should probably figure out some boundaries. So if ds is equal to dx times dy, we must find boundaries for each. So when we look at the x values, the x values are going to have to go from 0 to a maximum of r. So we go from 0 to r. The y values are dependent upon the x values because for functions y is dependent upon x. So for one, we definitely know that the minimum value of y is 0, but your maximum value of y is going to be dependent upon x. And so we need to be able to draw a relationship. It means if we have a certain distance x, like this, there's also going to be a certain distance y over here, and we can connect this and create a right angle triangle with the hypotenuse being capital R, or the radius. So that means the relationship is x squared plus y squared x squared plus y squared is equal to capital R squared. The reason why I'm using capital R squared instead of little r is because we're trying to find the maximum value of y, and so that's going to come with the maximum value of x. And the maximum value of x is going to be r, so we know that the maximum radius will be r. So this means y is equal to the square root of r squared minus x squared. And this means the range of y values will be from 0 to the square root of r squared minus x squared. So the next step, we have to integrate with respect to ds, which is equal to dx times dy. So if I'm integrating with respect to two different variables, that tells me I can't just use a single integral, I have to use a double integral. So there are two differential elements. So we use double integrals. So you might not have learned this before, but it's actually not something to be scared about. With double integrals, all we're doing is integrating with respect to dx and then dy, or vice versa. So one of the most important things is figuring out which one to integrate first. Do we integrate with respect to x or y first? My tip is to remember which one is your independent variable, because that one's going to come last. So if y is a function of x, y is a dependent variable, which means that we should probably integrate that first, and x will be our last one. When we're working with double integrals, we have some integral on the outside from a to b. Let's just make this a little bit easier. Our first integral is from a to b, and let's say it's dx. Then we have a second integral on the outside from c to d, and it could be integrated with respect to dy. So the way we would write this would be the integral of the double integral with respect to dx, dy, like that. So just remember, when you're working through these, you're trying to solve the integral in the center first, and you're going to work your way towards the outside. So that's the first one to solve, and then once you get the answer, you solve for the outside integral. So why don't we try that now? So let's set up our integral for the area of a circle. So we know that a circle is going to be 4 times the area of the first quadrant. So I have 4 times the integral. Remember, we said the independent variable is going to come last, which means it's going to be the outermost integration. So we put that here. It's going to be from 0 to r, because x goes from 0 to r, and then y goes from 0 to the square root of r squared minus x squared. And then we have dy dx. So the area of a circle is equal to 4 times the integral from 0 to r. We can solve for this. It's simply just y from 0 to r squared minus x squared dx. So the area of a circle is equal to 4 times the integral from 0 to r of the square root of r squared minus x squared dx. And okay, we're now here. This part doesn't look very nice. It means that we have to use trig substitution. Such as x equals to r sine theta, to evaluate the integral and get the answer. Do we really want to do this? Probably not. So to me, it seems like a lot of work, and maybe there's something more efficient that we want to use. So we're just going to leave it here and try out the other method. So I'm just going to make a little note here. Takes too long. Method number 2 is going to be polar coordinates. And in terms of polar coordinates, a really good analogy to use is a compass. So one that you would use to draw a circle. When you get a compass, you have two arms, they're closed, and the tips are together. And once you start with a closed compass, let's draw our coordinate system. Let's say you want to use the compass to draw a circle starting over here. So we have the origin. The closed compass's tip is going to be right here at the origin. And the first step is for you to open up the arm of that compass. When you open up the arm of the compass, you have a distance r that you open it up, and you arrive at some point over here. Afterwards, you'll probably realize that you have some sort of angle, phi, that it makes with the x-axis. And then you're free to rotate the compass around in a circle. So that means your compass is going to rotate possibly this way. So let's just draw the outline of a circle first. This would be what your compass would be able to sketch out for you. And that means we've moved a certain arc length here in order to arrive at our second point. So we've started off with an angle phi, and now we've changed. Let's put our r out here. We've changed by an angle of d phi. In terms of r, we do have a differential element we have to consider, and that's called dr. Because I can continue to expand my compass and pull it out, what I'm actually trying to do when I'm calculating the area of a circle is something like this. Your compass starts here. You're going to pull out the arm by a distance of dr, and this dr is supposed to be super small. You pull it out by dr, and you end up at this length. And then you trace out a circle. Then you're going to pull it out another distance, and trace another circle. So if my drs are infinitely small, then what's going to happen is I'm going to have a whole bunch of circles being traced out. And that is eventually going to fill up the entire circle until we reach our maximum radius of r. And that will be able to give us a good approximation to the area of the circle as well. So that's what polar coordinates can do for us. It's basically like creating different layers of an onion. So back to this drawing, it's important to know that there's going to be r, or dr, being pulled in the direction of r hat, and also, let's make this a little clearer, and we have d phi acting in the direction of phi hat, which is tangential to the curve. The other thing we want to note is that phi is called the azimuthal vector, or phi hat is called the azimuthal vector, whereas phi is called the azimuthal angle. So looking at the elements here, when we're using a compass to trace out different circles to create that big circle, to fill in the big circle, we have two variables. We just have r and phi, and that means only r is changing by a tiny amount of dr every single time, and the angle is changing by a tiny amount of d phi every single time. So the next step, similar to Cartesian coordinates, we need to be able to figure out a differential surface element. So we need to find out how to define ds with dr and d phi. So keep in mind the differential surface element is made up or defined by differential length elements. And this length is very important. If I'm looking at the radius, it's linear already, and it's going to give me a length. So that means that ds is going to be equal to dr. In order to get some sort of area, I need to multiply by something that's related to d phi, and d phi is an angle, so it isn't a length, but what is a length is what I've drawn in red over here, the arc length. So essentially what we're trying to do is figure out the area of this. So that's ds. So we have our r, or dr over here. So something like this. We're trying to find out ds here, with this being dr and this being the arc length. So since we know this is d phi, that means this is going to be the arc length, which is equal to r d phi. So if I wanted this black area over here, I would multiply dr by r d phi to get my ds. Okay, so now we have our differential surface element, which means we can go ahead and proceed with trying to calculate the area of a circle. So let's set some boundary conditions. We have our r values. If we look at the graphs we've drawn above, we know that the r value can only go from 0 to capital R, which is the radius of the circle. Then we have our phi values. With our phi, we want a full rotation around the circle, so that means it's 360 degrees, or 2 pi. So phi starts at 0 and goes towards 2 pi for a full revolution. So as you can imagine, if we're trying to figure out the total area of a circle, we pull our compass out a little bit and change the R value, and then we trace it around 360 degrees using phi. And then the more repeats you do to fill up the entire circle, that's how you're going to get the area. So we have A, the area of the circle. We still need to do a double integral. So we go from 0 to R, and then from 0 to 2 pi. And then we have R d phi dr. This is going to give us a circle from 0 to R. So I need to solve the inside first. It's R d phi dr. I know that R is a constant because I'm only integrating with respect to phi, so I take out the R, and that means I'm left with 0 to 2 pi of d phi dr. That gives me the integral from 0 to capital R of R 2 pi minus 0 dr. A circle is equal to 2 pi is a constant, and we have the integral from 0 to R of R dr. We have 2 pi R squared over 2 from 0 to R, and that gives us, the 2's cancel out, gives us pi R squared. So that gives us the area of a circle, and it's way faster than the Cartesian coordinate method. So how about another alternative or shortcut? So let's introduce an alternative here. Before, we used ds in terms of the differential elements, but defined by a polar coordinate. So ds was equal to r dr d phi, like we did. But using our analogy of a compass, in order to fill in a full area of a circle, we'd basically pull the compass arm a tiny bit farther after each revolution. So let's say I have this. I want to figure out the total area. Let's try this a little bit better. I want the total area of the circle, but at any point in time, we're going to pull the compass arm out by a distance of dr. So that means we have something along these lines. So this change in distance is called dr. We know the maximum is capital R. So if we drew a full circle instead of just looking at differential elements, if we were to try and calculate the area of this blue ring, the circumference would be 2 pi r. So let me just write this down. So change in radius is dr. The circumference is 2 pi r. And we can simply assume that the dr is supposed to be super tiny. So it's so tiny we can just multiply the circumference by the tiny thickness to get our surface element ds. So this is very tiny. Another way of explaining this is if we had this ring, what if we just cut it, unwrapped it, made a rectangle with a thickness of dr and a circumference of 2 pi r. That means we can get a surface element ds is equal to 2 pi r times dr. And then we don't even need double integrals. We can just calculate the area of a circle is equal to 2 pi times the integral from 0 to r of r dr. This is 2 pi r squared over r from 0 to r. And we have 2 pi r squared divided by 2. And this is pi r squared. So a true mathematician would subtract the area of the circles with the two different radii. So you would have one, let's say r2 over here and r1. A true mathematician is going to get the total area of the outer circle and subtract the area of the inner circle to get the total area within the ring. However, you end up with this dr squared term, which is even smaller than your super tiny dr, and it can really be neglected. So we use this approximation ds equals 2 pi r dr to simplify our lives. We still get the same answer. And remember, we are physicists and engineers, and we want to apply mathematical concepts in the most efficient and productive way possible. So what have we learned in this video? When we're working with polar coordinates, there's three things we should remember. Number one, the unit vectors are going to be r hat to change the distance, r, and phi hat to change the angle the line makes with the x-axis. Number two, the differential length elements are dr, which is a baby step in the radial direction, and rd phi, which is a baby arc length step. This means that the differential area element is dr times rd phi. So let's summarize this. We have the unit vectors, we have the differential length elements, and we have a differential area element. So the unit vectors are going to be r hat and phi hat. The differential length elements were dr, put that dr in the r direction, and we have r d phi in the phi. Wait, and then we have r d phi for the arc length. Next, with these two differential elements, we can create our ds, or our differential area element, which is r dr d phi.